All right, this is the intro video for AP Calculus AB, section 5.1, and we're going to be looking at the derivative of the natural log function. And so I thought maybe we could start off by defining what the natural log function is. That's right here. Ln of x is equal to the integral from 1 to x of 1 over t dt for all positive x values. So I'm guessing you probably haven't seen this before, so I thought maybe I'd prove it to you, prove that this actually is true. So take just a second here. Let's look at the calculator. Let's do a little test of this and see if it really is true. So go ahead and get your calculators out and we'll check that out. So let's start off just by doing something really simple. Let's just do like natural log of 7. So we do natural log of 7. Let's remember what that is. It's 1.9459, etc. And then let's do math 9 with that integral that we saw on the right side of that equation. So we'll go math 9 from 1 to 7, and then 1 over t would go inside the integral. Of course, it's going to show up as an x in the calculator based on the mode we're in, dx. And so these two are supposed to be equal to each other, and I think when you hit enter, you'll find that they actually are. So, on a really basic level, I hope that maybe proves to you, you can obviously do other test values, but maybe that proves to you that relationship really is true. We're going to base kind of everything we talk about on that relationship, basically the definition of natural log of x. So if that really is true, then we should be able to differentiate and figure out where we're kind of going today. So what I'm going to do is take that equation above, and I'm going to differentiate. I'm going to differentiate both sides. So we get d dx of natural log of x equals d dx of the integral from 1 to x of 1 over t dt. So the left side is really what we're looking for, but the right side, hopefully you recognize, hopefully you've seen this before. It happens to be Fundamental Thermocalculus Part 2. It's the derivative of an integral, and the integral has the upper limit being a variable, and so the rule that we follow here, the little trick that we follow, is we take the x and we drop it in for t, so we get 1 over x, and of course we do multiply by the derivative of what we dropped in, so that technically would be 1 times 1 there, but we probably wouldn't write that, so we can just leave it like that. So the derivative of ln of x is simply 1 over x. If we looked at this in terms of a chain rule, if the input for ln was something more complicated than just an x, we would get something like this. 1 over derivative of ln of u is equal to 1 over u times u prime. You just multiply by the derivative of the inside there. And just a reminder what the graph of natural log of x looks like. I'm sure you've seen this before, but maybe a good reminder for us. Natural log of x looks something like this. It's the inverse of an exponential, and it goes through the point 1, 0, and it increases for all of its domain. It increases from left to right, but it increases at a decreasing rate. In other words, that even though it continues to go uphill, it continues to trend towards flattening out, and so we get that pattern right there for the graph. And maybe that makes sense as far as connecting this here. Remember that the derivative is simply the slope of the tangent line. So the slope of the tangent line, in here is obviously very, very big slope, very steep. But as we go to the right, while still positive, the slope is going to be decreasing towards 0. And so maybe that makes sense when you think about the slope being 1 over x. In this region right here, all the inputs would be fractions, and so it would be something like 1 over 1/4, 1 over 1/8, and so that, of course, that flips up to be 4 or 8. So we're talking about a very steep slope. And once we get over into this region, once we get beyond x equals 1, then the inputs for x would be things like 2, 3, 4, 5, 6. Well, as those inputs get bigger, the denominator of the slope gets bigger. Therefore, the slope of the tangent line would be decreasing towards 0. And so, again, maybe just a little further explanation about the graph helps there. I hope that did. We're going to go ahead and look at a few examples involving derivatives of natural logs. So let's check those out next. All right, so the first one is the derivative of natural log of x squared plus 1. And so I think we can see that from the input right here that this is a little more involved than just ln of x. And so we will need to consider the chain rule. The chain rule is going to show up. And so the way this works is the derivative of natural log of u is equal to 1 over u. So in this case, our input is x squared plus 1. So the derivative would be 1 over x squared plus 1. And then we have to multiply by the derivative of that input, so it would be times 2x. We could write, of course, 2x over x squared plus 1, and that would equal the derivative of ln of x squared plus 1. And that's it. No need to go any further. Really, we can't go any further, I suppose. So, like always, encourage you at any point with these couple of examples here to pause the video, try it on your own, watch the video to see how you're doing. Do that at any point, and hopefully you find good success. Let's go ahead and move on to number 2. Number 2, once again, the input 3x, a little more complicated than just an x, so we will have to consider the chain rule. So ddx of ln of 3x, we're going to end up with 1 over the input, so 1 over 3x, times the derivative of the input, so that would just be times 3. So we could write 3 over 3x, and of course in this case the 3's do cancel, so you could end up with just 1 over x for this one. All right, and then number 3 here, ddx of ln of x to the 6th. Well, in this case it is just natural log of x, right? Natural log of x, but of course that whole function is being put into a different function, the 6th power function. So this whole thing overall is going to be a chain rule. I see 2 boxes here. I see the small box being natural log of x and the big box being the 6th power. So here's how this would work. It would be 6 parentheses ln of x to the 5th, that's just a power rule, times the derivative of the inside, so it would be times 1 over x. And if you wanted to be all technical about it, which I don't blame you if you do, you could put times 1. Of course, that doesn't change anything, so I don't see any reason to put that, but technically that's there. All right, and that would be it. That's the derivative of natural log of x quantity to the 6th. And of course, we could write it as 6 ln of x to the 5th all over x. Okay, we'll do a couple more examples to finish this up. Make that one more example. Number 4, ddx of x cubed ln of x. So take a minute, think about this. I'm hoping that it'll come to you what we need to do here. This is a product rule, and so we've got 2 functions being multiplied together. So once again, like the big focus is not just about the ln of x. Really, the big focus here is the product rule, and the derivative of natural log of x will be one little part of it. So what I'd write here is 1 d2, so the derivative of natural log of x is just 1 over x. There's 1 d2 plus 2 d1. Just using a power rule there for the derivative of the first factor. So x cubed times 1 over x is just x squared, and be plus 3x squared natural log of x. I don't know, I'm thinking of multiple choice. You might see the x squared factored out, so it could look something like this. Hey, who knows? It's definitely not a requirement, but it'd be good to know that could happen. All right, so that's it. Hope that worked out for you. I'll see you in class.